Our speaker for the next plenary talk will be introduced by our session chair, Professor A.J. Paramish. Sir, please.
Let's hope people are back. And welcome back to the plenary hall. And our next speaker is Professor Jun Lee of Shanghai Center for Mathematics Sciences. Yeah. And he'll speak on a proof of Yamaguchi-Yao conjecture for quintic-Calabi-Yao three-fourths. Professor Jun Lee. Thank you.
Thank you. It is a great pleasure for me to, it's a great pleasure and honor for me to speak in the 2021 BRICS. I will share with you the recent progress in our work in the Gromov-Witten invariant. And this is a joint work with Guo Sui from Beijing University and Huiliang Chen from Shanghai, Hong Kong UST. Okay, so this is about Gromov-Witten invariance of quintics. Gromov-Witten invariance is part of the mirror symmetry conjecture, which is challenging and influential. So it has it is started about the time when I was a graduate student at time of 1980s, and it is really initiated a lot of progress and become a big field in research in algebra geometry, symplectic geometry, topology, and so on. And Calabi-Yao threefold, I will mention the definition, but it's the first example is the quintic threefold. And for the Gromov-Witten invariant, the string, it's kind of an invariance for mathematician. It is, the string series has been leading the research from 1989 to 1993, from genus 0, Canderas, and genus 1, and BCOV Vafa, his group, and the BCOV Feynman rule, and the later is about the way to reconstruct the Gromov-Witten invariant potentials for all genus up to 51. And mathematician is catching up. In 1997, that's the proof, mathematical proof of genus 0 case, and 2007, the genus 1 case, and since 2018, there's progress toward proving the BCOV conjecture, Feynman rule. So the latest progress is led by two groups. One is Yongbin Ran and his group, and also the other group is our group. The major partner is the Guo Sui from Beijing University and Huiliang Chen from Hong Kong UST, and myself from Shanghai Center for Mathematical Science at Fudan University. Okay, so let me mention about the Calabi-Yau manifold. So it is a high three-dimensional analog of elliptic curves. We know the elliptic curve, the genus 0 case is kind of boring, and genus 1 has a lot of structure, and high genus at least 2 is kind of a general type, which is tough to study. But for the genus 0 case has a curvature 0, ridge curvature 0 case. And for the high dimension, it's for the 3 dimension, for the surface, it's K3 surfaces. And for 3 dimension, it is Calabi-Yau threefold. It is a smooth 3-dimensional complex manifold. It's a 3-dimensional complex manifold with H1 finite. H1 finite, then after you do a finite covering, become simply connected, and with also C1 equal to 0, the first Chern class trivial. And because of first Chern class trivial, by Yau's famous theorem, there is a ridge flat metric from the differential geometric point of view. So the first Calabi-Yau threefold is the Fermat-Quintic threefold. It is a hypersurface inside CP4, which is defined by a degree 5 polynomial. Indeed, I mean, for most of the degree 5 polynomial which gives a smooth hypersurface, the Gromov-Witten invariant are all the same. So let's just fix the one which is the Fermat-Quintic threefold, the simplest, which is x15 plus, or just the fifth order term from x1 to x5, sum equal to 0. So this is the Fermat-Quintic threefold. And this is something, well, I don't know. No, it's just getting complicated and simple enough, complicated enough just to eliminate the thing we think about, but it doesn't really help. So what is the Gromov-Witten invariance of quintics? So in a way, in a nutshell, for now, we just look at the moduli, the space, we count the space of stable map, holomorphic map from a Riemann surface for algebraic curve, complex algebraic curve, to the quintic Calabi-Yau threefold X. X is the Calabi-Yau threefold. Okay, and we look at the moduli space. I'm writing this as a moduli space. Moduli space, all the F. F is from a smooth curve, and that's the interior part. And when we do put a bar there, it is all stable curve. It is a nodal curve such that the image curve has degree D. Okay, X is a hypersurface in P4, so it has a degree. So we fix a topological class of the map, and then we say F is stable. F is stable simply means that you cannot just keep inserting a rational curve into the curve. So just the automorphism of the map is finite. Okay. Put it another way, is something that makes the moduli space relatively okay, workable. Okay, so this is a compact proper moduli space. It's a Deligne-Mumford step which has finite automorphism but doesn't have infinite automorphism, because automorphism is always finite. It's a stability. So the ideal case is when all stable maps are isolated. For instance, if you perturb the complex structure, then you will make all the holomorphic curve. Well, that's how this Tian and Rand did their construction in the syncretic category. Is they deform the almost complex structure so that all the pseudo holomorphic map inside are isolated, rigid. There's no deformation. So then only finitely many by dimension count, there are only finitely many maps into the Calabi-Yau threefold with deformed complex structure, and then you just count all this number. So Gromov-Witten, in the ideal case, you just view that ideal case, the Gromov-Witten are just the number of stable maps. Right? G is the genus of the curve, D is the degree of the map, and X is the Calabi-Yau threefold. Okay, But otherwise, in general, in algebra, when we try to stay in algebra geometry, you can never ask such a nice thing always happen. So we have to do the virtual cycle. Virtual cycle is a way to do this topological theory in algebra geometry. This is developed by Tian and myself, and also Baron and Fantaki use the cotangent complex language. So the actual definition is the degree of the virtual cycle of the modular space. Okay, just take this and something that can be worked out, but it is very difficult to calculate explicitly. So historical development is, as I mentioned, it's led by the mathematical physicists, and it's the generating function of the quintic. So we are only talking about quintic. So I left out the quintic x explicit. So so it involves, you fix the G, right? You fix the G, but you let the D grow. And for every D, you put a Q. Q is just a variable. So you recorded the number of the genus G degree D chromophoton invariants with fixed G. Then you get the FG, which is the generating function. This is an infinite power series. And in 1989, Candelas and his group derived F0 explicitly. Okay, so he basically write down a formula and say, okay, this is the way to get this one, and that's really shocking. And that's the 1989 by mirror symmetry. Okay, what is mirror symmetry? Okay, let me just mention this. Mirror symmetry using the word of Varfa in his 1998 ICM-Plenary talk is a very difficult mathematical problem. So calculate all degree D chromophoton invariant, counting holomorphic in Calabi-Yau-Swift gets transformed on the mirror to a question involving the variation of Hodge structure. Okay, so that's the mirror symmetry, and it is just transform a very well-defined mathematical problem in enumerating geometry of algebra geometry to variation of Hodge structure, which is a kind of difficult and well, actually the calculation of variation of Hodge structure is much easier from the physics point of view. But the point is to get transformed. This is really like a six-dimensional analog discussion, and there's no logic behind it. So what we say is that whatever the Candelas formula F0 has been talked about is the conjecture, right? Because from our perspective, but in 2 years, 1991, BCOV is Varfa. BCOV, they derive F1 right, explicitly of the quintic, more than quintic, but for quintic they derive explicitly. And 1993, they constructed the BCOV Feynman rule for FG. I won't be talking about Feynman rule, but that's something amazing. And then 2009, Clem is kind of a mathematician when I know him. So so explicit method to get FG for G up to 51. Okay, they didn't get a closed form, but they have laid down the explicit method how to get this. But somewhere, quite a few key steps, they involve something which we don't understand at all. So let me just mention BCOV Feynman rule is a finite combinatoric algorithm determine the generating function up to 3G minus 3 constant. So up to 3G minus 3G constant, we can sort of determine the whole things. So this is his work. Now, what is mathematics? In 1997, Giventhal and Liang Liu Yao, the two groups proved the genus equal to 1 formula. So mathematically proved the formula. And 2004, Yamaguchi Yao conjectured the functional equation. This is the equation we're going to mention how to prove it. And then in 2009, Zinger proved the G equal to 1 formula. So this is so far the progress. Okay, I mean, so you think about it, 97 and 2009, and here genus 1 is 91 and genus 0 is 89. So 10 years after the genus 0. But for physicists, from genus 0 to genus 1, they took 2 years, and for us, 10 more years from genus 0 to genus 1. Okay. Okay, now let me explain the Yamaguchi-Yao conjecture. Okay, so when I look at these slides, I mean, my mind is can become spinning. I mean, the point is that you can define the the pink label. These are become a power series in Q. Okay, and J is a power series. Y is a power series. You expand it, and I11 is a power series. And then A1, AI, BI, X. So they just you just think of this as a power series. You can if you sit down, you can have a way to write them down in a way that is reasonably explicit. And what do? You're setting for the genus 0 and genus 1 because of the automorphism. You have to modify the constant term a little bit. But the point is that FGQ, Q is a capital, Q is I use the capital Q, is basically give you all the chromorphic invariants, right? And 0D and 1D and GD, right? So G bigger than 1, you have all the FQ. And then you have PGN. PGN is another polynomial. I mean, you just modify. This is all told us by the physicists. Okay, so you just do this, and then the point is that once you know the PGM, you know the FG, and of course you know the FG, you know the PGM. So knowing PGM will give you all the information you need about the FG. Okay. So the Yamaguchi-Yao's polynomial structure conjecture is that the PGM, this infinite power series, which is kind of a way of rewriting the chromorphic invariance of genus G, and less chromorphic invariance involve chromorphic invariance of genus G and those of less than G, genus of less than G. Okay, it lies in the ring A, B, B2, B3X. Okay, these are the. I mean, I'm not going to come back, but these are the polynomials I just mentioned. You can explicitly write down, right? And these are the power series we mentioned before. And the PGM is the polynomial that you can recover from PGM. You can recover F. So basically, we're saying that the Yamaguchi-Yao polynomial structure conjecture says that the relevant invariant we need to know actually is in the ring of a ring generated by these 5 explicit polynomial. So basically, this is a finiteness conjecture. So if you know the explicit form, because if it's a ring in only is a polynomial ring of these 5 polynomials, so it will involve a couple of coefficients, involve A, B, blah blah. And then if you know that these coefficients, you know the P because you know A, B, and BI, right? And once you know the P, you know the F. So this is a finiteness conjecture for the chromorphic invariance. So Yamaguchi-Yao polynomial structure conjecture is a finiteness conjecture on the chromorphic invariance of quintics. And the main theorem is that Yamaguchi-Yao's polynomial structure conjecture holds true for quintic Calabi-Yau 3-4. And this is online, it's already accepted and it's already appeared online on Annals of Mathematics. Okay, let me try to explain the proof. What is the proof? Okay, so so there's a Rosetta Stone. I know everybody knows this story. And from the stone, we get the hint. And from the hint, we try to make sense of the hint. And from our way of making sense, we found the way to prove the theorem. So that's amazing. So it's what is the Rosetta Stone? This is the Rosetta Stone. It's a stone. Well, actually, it's a one paragraph, 1 line or 2 lines from Witten's research paper. So there is a continuous family of conformal field series. So this is the Rosetta Stone of a conformal field series interpreting from Landau-Ginzburg to Calabi-Yau. The CY and LG correspondence arises upon examining this relation in the presence of a particular common superpotentials. Okay, so here are the keywords: Landau-Ginzburg, Calabi-Yau. Okay, and there's a Calabi-Yau Landau-Ginzburg correspondence, and there's this common superpotentials. Okay, so from reading the Witten's paper, you kind of get a sense that Landau-Ginzburg should relate to the FGRW invariants I'll mention shortly. And Calabi-Yau should relate to the Gromov-Witten invariants. And the correspondence, something like a transition, interpolation, or wall crossing if you do the algebra geometry. And common potential, superpotential is the LG function, which led to cross-section localized virtual cycles. And this, all of this, by looking at the stone, by looking at the keywords, by trying to make sense of the keywords and based on our experience and blah, 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 after all the work, it led us to the introduction of a new field called the NMSASP field. Okay, let me try to make sense of what I just said a little bit more. What is the LG function? The LG function is P times x1/5 plus x5/5. So it's just a Fermat-Quintet polynomial plus a P. One end is, so this is the LG function, and the Witten's word says that there's two ends of this function, right? One end is the Gromov-Witten. What is this? So we take the Gromov-Witten invariance of x/5 of the Fermat-Quintet hypersurface inside P4, and we take the stable maps, and we take the virtual cycle, and then we take the generating function. But why is that, right? Why is that? Okay, let me do the other one. The other end is the FGRW. FGRW is the, okay, you take, instead of the moduli of Quintet Calabi-Yau 3/4, you just do a polynomial, and then you do the 5-spin curve. 5-spin curve is a curve with a line bundle. So the line bundle is isomorphic to the canonical line bundle of the curve. Okay, well, you may have to add some marking, and you have to allow the orbifold structure, so it has to be a stack curve stack. But that's just technical. Okay. So how these two theories become the two ends of this LG function? So that's our way of interpreting. So we rewrite the theory for the Gromov-Witten invariance of X. We, instead of just say a map, well, it's a map to P4. A map to P4 involves 5 sections of a degree D line boundary if the map is degree D, right? So we just look at the stable map with field. So we have slightly changed. We instead of X, we put a P4 here. Instead of on the shoulder, we put a P there. So this is C is the Riemann surface, algebraic curve, genus G, okay? And L is a line bundle on the curve. And then phi and rho, these are sections. Phi has 5 sections, 5 copies of section of L, so L/5. And rho is, okay, here is tensor with omega c. This is tensor by gravity. This is what we learn from physicists. And that is extremely important, okay? So you just look at this one. And if you look at this becomes a field theory on curves. So it's a semi-linear theory, right? It does not involve a map into a highly nonlinear space, but it's kind of almost a linear space, like a projective space, okay? And then you just take a section of line bundle, and there's a curve. Of course, curve is nonlinear, but it's degree, which is dimension 1 nonlinearity, right? So we call semi-linear theory. So stable map with field, which is just, if you take a stable map with field, we have C, we have L, we have phi never zero, right? We want it to never zero, okay? But if phi is never zero, phi is going to define you a map into P4 and then couple with the field. So stable map with the field is just, okay, let me try again. So original we say this is a curve with a line boundary with a bunch of fields, only fields. But now all of a sudden we say, okay, this has become a stable map, C to P4 plus a rule field, okay? And here is the theorem. Suppose the obstruction theory has a cosession. So I'm not going to rewrite the whole theory. This is the way we prove long before this project began. So it's with King. Then the cosession localized virtual cycle. There's a cosession localized virtual cycle. The cosession is the one given by the LG function. Is equivalent to its ordinary virtual cycle. Okay, and the point is the second theorem is that the cosession localized virtual cycle of the modular stable map with field has, this is the cosession localized modular virtual cycle of the modular space is the NGD. NGD is just the Gromov-Witten invariance. So we can rewrite the Gromov-Witten invariance of the quintet. Quintet is highly nonlinear space, subspace of a P4 into a semi-linear theory on the modularized space of stable map with sections. Stable maps to P4 with sections is a semi-linear theory. So this really is transforming a theory into a semi-linear theory. So let me just re-summarize. The LG function, a seemingly simple idea, found its beautiful role in the forming of cosession localized virtual cycle to get theorem of Chen and myself. And this transformed a nonlinear theory to a semi-linear theory. The nonlinearity is pushed under the rug, the virtual cycle. So by using the virtual cycle, so the nonlinearity of, say, a map going into the quintet 3/4 is disappeared. All what's left is we have to do a virtual cycle, the cosession localized virtual cycle. The cosession involves the quintet. So the quintet property, the nonlinearity from the quintet is going into the virtual cycles. Okay, what about the FGRW invariance? Well, FGRW invariance is the we mentioned is about the spin curve. What is a spin? Spin is rule is isomorphic, right? We mentioned the spin is that what is the spin? Spin is L to the power 5 isomorphic to omega. Okay, so it's an isomorphism. So isomorphism can be just turn one line boundary into the dual, so become a section of L minus 5 tensor with omega, right? And okay, it's isomorphism, so it has to be a nowhere vanishing section. So rule is a nowhere vanishing, never zero. So phi is never zero, but phi is a 5 section, so never zero is become a map. So rule is a nowhere is a line bound, is a section of a line bound. It is nowhere zero, so it become make the line boundary trivial. So rule is isomorphism, just rule is never zero, and then we can conform this moduli space 5p. Okay, so what I'm sigma is just marking. Okay, with this time we have to have it, but let's just forget it. So we have C, we have L, we have 5, we have rule, and 5 is 5 section, and rule is isomorphism, and isomorphism can be seen. So this is just like before, right? It's a stable map with section, but except that before we say 5 is never zero, but now here we become rule is never zero. So here is the point. The point, if we form this construction and then we work a standard obstruction theory of this one, then this construction provides an algebraic construction of the narrow FGRW invariance. So it's not, I mean, the upshot of this theory is not that we give a new construction, but rather that we give it a construction that's parallel to our rewriting of the global fitting invariance of printing. And now the next one is that the Rosetta Stone say that the two ends of the, so the Witten's work say that two ends of the family of the series are global fitting invariants of the printings associated with the same LG function. So this is the key point, associated with the same LG function. So we see the two sides are series of moduli of C sigma. Sigma is the marking. Just forget about the marking and just focus on C and the line bound of L, and there's a rule and then phi. And the stable map is your phi is never zero. Phi and rho are the same, right? You see phi and rho are the same, but only the stability is different. So global fitting invariance, you only allow phi which are never zero. Five sections are never zero, no common zero. Okay, but the FGRW is that you only allow rho to be never zero. Rho is a section of one line bundle, so it's never zero, meaning the line bundle is trivial. Okay. So this actually associate to two GIT quotients of this Arding stack quotients. The two GIT quotient is one is you're taking away the one unstable locus is by C5 take out of the minus zero. The other one is taking out the C minus zero. And the quantization of this, because you have a C star action, so you put a line boundary here, and then you put a curve, you put a line boundary, and then you have a rule which is associated to C, right? And then this phi, which is C5, and because you subtract zero, your phi is never zero. And here you have C minus zero because rho is C, and because you take out zero from C, rho is never zero. So what we are saying is that all of a sudden you realize these are just a baby case, but these are the two quantizations of the two GIT quotients of one single Arding stack quotient. Okay, so this is everything. This is, we are still trying to make sense of the Witten's works. Okay. And now what do we want to do? Because Witten says that you need to study the transformation from one theory to the other. And if you think about it, then the way you do is you construct a master space which interpreted two theories, and using the master space to study what is the master space. The master space interpret these two GIT quotient is the GIT quotient of this huge. You just add a P1 into the above Arding stack. So you look at this. So here you look at this, the C5, C are the previous copies, and the extra C cross C are the P1, C2, okay? And the weight, because you add one action C star. Originally there's one C, so you have two C star action, and then here are the weights acting on this one, and you take semi-stable points. Semi-stable are F, U non-zero, P, V non-zero, and U, V non-zero. So these are not common, not both zero in this case. So these are stability. Now what do? We quantize it. We're quantizing the master space. We obtain the MSP fields. Okay, the MSP field is coming from quantizing the master space relating the global fitting invariance and the FGRW invariance. So, okay, so if we look at this one, we see sigma is just marking, okay, so CL, but we have, because this time we have two. The thing we learn is that once we have one copy of C star, we have to put a one line bundle. Now we have another C star, we have two line bundle, and here are the weight. So this actually gives you the line bundle where the sections is belong to. So here you have L, you have two line bundle, you have 5 rules. These are the 2 previous sections, and you, because of a 2 more copy of C added, we have to put 2 more fields, which are mu and lu, and because of quantization, these are all sections of line bundle over C, okay? Well, C, L, phi rule are the old stuff, and N mu V is the P1 family over C, which is a line bundle plus blah, blah, and such that these are nowhere 0, right? This is a stability condition. These are the stability conditions. I mean, the stability condition is written before, so we have nowhere 0. So in other words, the M mixed spin P. So mixed spin is the spin, the FGRW, where P field is the one which is coming from the giving the Gromov-Witten invariance, right? So these are the sigma is the marking, CL is the old stuff, phi rule is the old stuff, and the pink one, the red one is the N and mu. These are the new stuff, and phi and rule are the old, 5 section from L, and minus 5 tensor with omega, which is tensor omega is the tensor by the called twisted by the weight, gravity, right? And mu and nu are this Ln and ny is Ln and n. Well, if you look at this one, right? This is 1 and this is 1, so that tells you everything. Such that these are nowhere 0. So these are the mixed spin P fields. Okay, so it's a curve with a marking, but it's a twisted curve. It's a Deligne-Mumford stack curve with 2 line bundle, 2 invertible sheaf on it, L and N, and with a bunch of sections, 5 rule, mu, and nu, and the sections are written as such. And such that the stability conditions are that we say stable mixed spin P fields are when 5 and mu together has no common 0, and lu and nu together has no common 0, and mu and nu together has no common 0. Okay. So here's the theorem. The theorem is that the modular mixed spin P field is a C star Deligne-Mumford stack with a compactly support C star equivariant virtual cycle, and the localization form, because it's a Deligne-Mumford stack with a virtual cycle, and which the virtual cycle is C star equivariant, so we can get a localization formula, and the localization formula provides a collection of polynomial relations among the Gromov-Witten invariants of the quintic and the FGRW invariants of the quintic Fermat polynomial. Okay, so this is well. Okay, proof. How to prove? Well, the point is we just look at the fixed loci. The fixed loci are the 3 cases. There's a mu equal to one field is mu. One case is the first case is the mu field is 0. If the mu field is 0, mu v is never 0, right? So v nu has to be nu I or v. V has to be equal to 1, but it's a line bounded, so it's a constantly 1 section. And if this the phi is never 0 and rule is arbitrary, it gives Gromov-Witten invariant. The other case is gives the FGRW invariant, and the third case is the Hodge integral on MG. So the key point, the localization formula gives an interpretation between Gromov-Witten invariance and the FGRW, right? So this is this. Okay, so then we go on to, because of our aim, I mean, our first aim, of course, is just to get a relation, but then we get ambitious, so we want to crack the Yamaguchi-Yao conjecture and further the BCOV Feynman rule. So with Guo Sui joining our group, we further introduced NMSP field. Okay. Now the point is that mu, instead of 1 mu, we put N mu. Mu are all the same from the same line bundle. With mu1 up to mu n repeated n times. Okay, I don't have a proof because I mean, passing rule has no place in the no place in the definite or mathematical rigor. It's not been defined mathematical rigorly. So, but it feels like using MSP field to approximate a path integral n, let n goes to infinite. Okay. So use the theory of NMSP. We have proved Yamaguchi-Yao polynomial structure conjecture hold true for quintic Calabi-Yao 3-4. Well, the proof is apply the theory of NMSP fields and work hard. It is accepted. It is appear on the Annal of Mathematics. It's online 2021. We also proved the BCO refinement rule hold true for quintic Calabi-Yao 3-4. And this is in archive. And thank you. Thank you.
Thank you very much for this inspiring talk. And are there any questions from the audience here or from the online audience? So, if not, I have a small question about the orbital invariant. So, when you defined it, you used the C, L, phi, and rho.
Yes.
And the phi was never identically 0. And what was the condition on rho for the
Oh.
invariant?
Rho is this section, the section, okay, this rho is okay, so here is the thing, right? Because this is weight 1, so it involves line bundle 1, right? This is weight -5. Weight -5 makes the minus L tensor -5, fifth power come in. But then you have to twist by gravity. This is what we learned from physics, okay? So this is the rule, and the rule is going to be.
Can you see the first definition? It was much before. First time when you introduced.
This one. Oh yeah. So the 0 is that's a tricky part. So if we do this, if rho is never 0, rho makes this one is identity is a trivial line bundle. So this L to the power 5 is isomorphic to omega c. This is the spin 5 spin curve. And this, the Gromov-Witten invariant case, is you let the phi never 0, which gives you a map, but then the rule is just use this rule to allow you to do the virtual cycle, cross-section localized virtual cycle, and which give you the Gromov-Witten invariant. That's really mysterious.
It's like a circular of the exterior, right?
Hmm?
It's the circular of the exterior, the H0.
Which line?
H0 of L dual tensor omega, right? So
yeah, tensor,
yeah.
Yeah, I think it is, yeah, it's tensor -5.
Yeah, so it's the H1 of the circular. So you're making some statement about the H1, or is that giving you the stability? Because when you interpret it as a map to P4, you are saying it is stable map. That's what
the stability is just this is so simple. This is stability. Stability, you quantize this stability just taking out of the origin, right? But if you quantize it, you make it, this stability makes the phi never 0. 5 is 5 section, right? 5 section.
And this already gives you a map, right? That alone is enough to give you a map.
Yes.
So what is the stability of the map?
Oh, this is the let's see. Let's my mind. Okay, I see what you try to say. or we still put the automorphism finite? Yes.
Yeah, so.
Yeah, yes. We try to emphasize the LG function here in this slides.
So is your C irreducible? Like, for instance, if the genus is greater than or equal to 2, then of course automatically.
Oh, we still say it's a no, that's a okay. So okay. So the spin case, you have to make the curve curve stable, and okay, you just make the automorphism finite. Yes, automorphism finite.
Okay.
Yeah.
So that will be kind of an extra assumption there.
Yeah. So because the MSP field, original MSP field is just make the non-zero plus automorphism finite. I didn't write the automorphism finite here. It's just because with a curve, with line bundle, and with section, you can define the whole package as self-automorphism. Yeah, you make this non-vanishing property plus automorphism finite. Yes, thank you.
Yeah, thank you. So if no further questions, let's thank the speaker again.
Thank you.